whatever, rest or whatever, wait for the next class. Because I know that you're used to having a holiday today. Because in schools it used to be that way. Here we have only one holiday. Okay. So we have done two methods till now. One is bisection method and the other is false position method. And now we are going to do what is called as secant method. So the secant method has some things in common with the previous two methods. Is the screen visible? I just want to have one confirmation.
Yes, sir.
Yeah, thank you.
Yeah, the screen
So
is visible.
secant method, yeah, thank you. So secant method has a couple of things which are common. Number one is that here also you have two assumptions. Uh, this is common with bisection and false position. The second thing is that here also there is a linear interpolation, which is common with false position method. But then now something very drastic happens here, and that's why this what and whatever drastic I'm going to tell you that happens in this method is what ensures that the convergence is faster, but you're not always sure that there is convergence. So it's like it marches to the solution, and then it could just be that it is marching away from the solution. So you don't really know. So this first step in secant method is that choose two initial approximations. So those initial approximations are x1 and x2. Okay, and here the difference is, and then of course you choose upside. Now in this case there is no need to check whether the root lies between this interval or not. You can just start with any interval. That is what it is. So that is the kind of a danger here, because you don't know uh, where you're starting with. So second point starts is like no need to check if the root lies in between the proposed interval. That means we will not check fx1 dot fx2 is less than 0 or not. We are not bothered about it. So now you have 2 points which will be x1 and fx1 and x2 and fx2. Then the third point is using linear interpolation you find x3. So you know what linear interpolation we are talking about. It's a straight line thing that we did in false position. Using linear interpolation, find x3. And what's that value? That value is, it is x1 fx2 minus x2 fx1 fx2 minus fx1. Once you find this value, Then you can check, uh, you can check fx3 is less than epsilon. In this case, probably this would be the best thing to check, not x1 minus x2 less than epsilon. This is the condition to check in this case. Check this. And now in the fourth step, you discard x1 altogether, new interval becomes x2 and x3. That's, and then you proceed. You forget about x1. Now next interval is x2 and x3. So then what will happen is in the next iteration you'll find x4. Then the next interval will become uh, x3 and x4. Then you'll find x5. Then the next interval will become x4 and x5. So it's like you're marching in some direction, whether you're going forward or backward, and you constantly keep checking whether that fx3, fx4, fx5, fx6, whatever it is less than epsilon or not. And if it is, then you stop. But if it is not, then you run for certain number of iterations, and you realize that your solution is not converging, and then you stop there and say that you've not obtained any solution. Then maybe you can go back and revise your x1 and x2 to begin with, and then start the process again. So that is what it is. So convergence is not always assured. Therefore, we put a limit on the maximum number of iterations. Okay, so I'll write that. So in this is an important point I want to make here. That since, and then this is like after step 4, you just repeat things. So since the convergence isn't always guaranteed or assured, is assured, we put a limit to the number of iterations. Because it could just so happen, like for example, I'll tell you what I mean. It could just so happen that suppose this is your function, it is cutting here, and let's say that you chose, okay, so this is your x, this is your fx. You want to find this root, right? This is your solution. But suppose you took x1 here and you took x2 here, and then your x3 came out to be something here. So then x2, x3, then you come here, 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 and you're marching away. Then you never come to this point. Yeah, you're going away from this point. Then so you have to stop your this thing, your code after a some point, because then you are not converging to the solution. And convergence is fxi plus 1 is epsilon basically, right, for the ith iteration. So if this is not satisfying after say 100 iterations, then you'll be rest assured that you have not got the solution, and then you stop and then you choose some other reference points of explanation. So this is why this method is kind of risky. But then if you somehow choosing the right interval, there could be fast convergence. Of course, there is another thing. It could just be that, like for example, you're solving a cubic equation, you're solving a fourth order equation. You may start at two intervals. You're looking for some root which may lie between those two intervals, but you may just end up with some other root. So if I suppose give a problem like this in the exam, and I ask you to find a root without I giving you an interval, then it could just so happen that different people will come to different solutions, right? Because they'll choose some initial interval. Whether one root will lie in that interval or not is completely dependent on what you choose, and then you may just reach some different solutions, because we're assuming that that equation will have three real roots or maybe two roots or whatever. Okay. So this is what it is. This is how it goes. Let me just kind of let us solve numerical on this, and since this numerical is it's a shorter number of iterations, so it will be nice if you people solve it along with us solving it. So I'll ask the values, and somebody should tell me the values. So the question is, an equation like cos x minus x e to the power x equals to 0. This is a transcendental equation, right? And I say that, I'm telling you that there is a root that lies between 0.5 and 1. The reason why I'm telling you is that you can just then compare the number of iterations of this method with the number of iterations of bisection or cos fusion. You will see they're much lesser. Okay? So we want to find the root which is correct up to 3 decimals. So the question is, find the root which is correct up to 3 decimals. Okay. So iteration 1, x1 is 0.5, x2 is 1, fx1, please tell me the value for fx1.
0.292855.
I'm sure, because I have a different value. Check again. Is your x in radians or degrees? Yeah, it should be radians. What's 0.5? Put me later. Just a second, let me also check it. So cos minus 0.5 e to the power of 0.5. Yeah, I know. So ये है, so whether mine also has radian service to this. Let's see. This is 0.8775 minus 0.5e. So मेरा भी बड़ा है, वो पॉजिटिव नंबर, but it's negative. कुछ कितना है? Yeah, it is coming out to be 0.0532. Yeah, that is what I have. So I think even in my calculator, it's in the distance degrees. So this value, I should say, this actually comes out to be 0.056. 0.5.
0.56.
0.0532. You see what I mean? It means check this is the value that I'm getting. Then fx2, I just want to tell you what it is. So this is coming out to be cos 1 e to the power 1. So this is minus 21780. So you can be rest assured that the root lies between these 2 points, because if you do a multiplication of these, you get a negative number. So the root lies between them. Then you calculate x3, and the x3 is evaluated as fx1, fx2 minus x2, fx1 whole divided by fx2 minus fx1, and this value comes out to be 0.5119. Then you check fx3. What is this value? fx3? fx3 will be cos of 0.5119 minus 0.5119 e to the power of 0.5119. This value comes out to be 0.0177. Of course, this is a small value because we're looking for e to the we're looking for three decimal places. So this should at least be less than 10 to the power of, let's say, minus 2. Okay? So, but this is not, right? So we will proceed further, and the new active, the new value, the new value interval will now become x2 and x3. So there is just a reverse order. It's written like, this looks absurd to you, 119. But this is like a backward interval. You don't really need to worry too much because you calculate x1 and you calculate fx1 and fx2, and you put it in the formula. What is first and what is second doesn't really matter. So in this case, x4 becomes your x2 fx3 minus x3 fx2 divided by this minus, but let's just do this to avoid confusion, lot of x's. So this is your new interval. So now let's say that this becomes your x1 and this becomes your x2, so that we are always talking in terms of x1 and x2. So in that case, your x3, I should also probably write it like this, x1 and x2. So now your x3 becomes 1 into f 0.5119 minus 0.5119 f1 divided by f 0.5119 minus f. So you get x3, and that x3 comes out to be 0.51. Okay, then you check again. You get x3 as the value that you get is 0.058, and this is also not less than 10 to the power minus 4. So we proceed further in the third iteration. Now our x1 and x2 become 0.5119 and 0.5158, right? So basically what is happening is you pick up this value and you pick up this value. So this gives you the interval. So now you find x3. So x3 is again the same formula to apply. So your x3 would be 0.5119 f 0.5158 minus 0.5158 f 0.5119 whole divided by f 0.5158 minus f 0.5158. And if you do this, you will get the value of x3 as 0.517. Now you check. When you check this value actually comes out to be 0. So this is your answer. So you get the answer in third iteration. It just so happens that you get an exact answer correct up to 3 decimals. So this is what it is. Right. So this is how you will proceed in this method. I give you another problem. You can try to solve it. So the problem is like this. The problem is x cube minus 5x plus 3 equal to 0. Find the answer correct up to 3 decimal places. So I'll just give you one interval. You find out the root which lies in the center. So you can find out using this method again, and I'll give you the answer also. So the answer is going to be x is equal to 0.656. Okay, so that's it. We'll stop the class here today. Just do this. We'll do Newton Raphson after pooling in an offline class, and then we'll write codes in the next class, and then we'll close the same. So the same will also be over. Okay. All right then. Happy Holi to all of you.
Happy
Hey,
Holi.
and stay safe and enjoy your
Happy Holi,
festival.
sir.
Bye bye.
Happy Holi, sir.
Happy Holi, sir.